Good morning, good afternoon, or maybe good evening. This is Gary again with Colorlight. I'd like to thank you all for taking time joining us. Our subject today is advanced parameters in LEDVISION software. My plan is to do this subject in 2 classes as there are so much things to cover. This is the first class. Before we get started, there are some points I should make. We're roughly doing 30 minutes presentation. If you have a chance to type the questions in the chat window, please do so. We've got a team of engineers are standing by answering questions in the chat. I will also keep an eye on that as we go, but I'm not going to focus exclusively on the questions until I get towards the end of the broadcast. We are recording this session, and this recording will be available online shortly after the session ends. So make sure to follow us on Facebook, LinkedIn, or YouTube to receive our latest course and technology information. You can also send us your feedback to my email. We will be glad to hear your suggestions. Let us know what you want to hear and what you want to see in other sessions. We will keep improve this and make this better. Our focus today will take on few frequently configured parameters in LEDVISION software, which affects LED screen's performance. In the beginning, we are going to discuss how LED screen works, just to provide you a background to understanding the technical terms used in the software. I'll explain these terms definition, and then we will get an overview of the LEDVISION software user interface. But we will not go into details of how to use LEDVISION software, as is not our object today. Our goal for this course is to help technicians understanding adjust LED screens advanced parameters through LEDVISION software. And lastly, we will have a Q&A session in the end. I will review the questions in the chat and try to get them answered in real time. As we all know, LED stands for light emitting diode. LED screen uses an array of light emitting diodes as pixels for video display. Nowadays, a LED screen are made up of millions of LEDs. The controller is like the brain of LED screen that organizes millions of individual LEDs and make them to be presented as an image. Here I'm using this schematic diagram to help you understand controlling LED screens. In this example, LED screen represented as a 4x4 LED matrix. Each one of these LEDs in the matrix as represented by a LED symbol, this triangular thing. In order to understand how to work with one of these, we need to know a little bit about how LED works. LED is basically one-way valve for the current. In other words, it only allows current flow from the anode to the cathode, doing so to eliminate the light. By arranging the anodes, which is the positive side, and the cathodes, the negative side, in a particular way, we can achieve a matrix and call upon each LED individually by sending high and low signals from the receiving card. So basically, if we want to turn on the LEDs on the first row in this matrix, the receiving card needs to send a high signal to the first row through MOS IC. And send the low signal to each column through the driver IC, the bottom side. In the same way, we can illuminate one row at a time from the top towards the bottom in this matrix. It starts from the first row, then the second row, and the third row. and then the fourth row. But notice that each time only one row can be illuminated in a very, very short time. The LED on time measured in microseconds or maybe even less. After row number 4 illuminated, then start the next cycle from the top row to the bottom row and repeat this cycle over and over again. Imagine that if this cycle is completed in 4 seconds, so each LED's on time in a row is roughly 1 second, your eye would perceive it as flashing. Now, if this happens fast enough, then your eye doesn't perceive it as flashing, but rather perceive it as on. For example, it's just like setting the camera. If you take a very slow image of a car on the highway, then you can see the lines of the headlights. Similarly, your brain can interpret the lights flashing that long, so you have persistence called persistence of vision, and you only see it as on. By doing so, we can make any combination of on or off LEDs in a LED screen to create images and animations. This schematic might not be exactly coincident with the actual LED real working state. This example is simply meant to give you a brief image of LED screen working principle. Just keep this in mind. LED screen, the LEDs does not stay on all the time. They are flashing lights. All right, let's look into some of the technical terms that frequently mentioned in LED screen performance adjustment. Grayscale is definitely one of the most. What exactly is grayscale? Grayscale is the luminance variations from the darkest to the brightest of an LED. Technically, brightness and grayscale are not the same thing, but you can think of grayscale as brightness level if you wish, because there are some similarities between them. Let me take an example here. If the receiving card receives 8-bit data, so its input grayscale is 255. Because LEDs are linear, the receiving card will not directly output grayscale as it received. The receiving card converts each of input gray level to a certain value. The values after conversion are the output grayscale. Normally, the input and output of low gray levels are the same. Like the gamma table showing here, the output gray level are the same as the input until gray level 40. After 40, the 41st input is mapped to 44th, and the 42nd is mapped to 45th. We can either edit the gamma table or the gamma curve through LEDVISION software to modify the mapping between the input and output. Depending on the type of driver IC, there are different gray levels we can set up in LEDVISION software, such as 4096, 16384, 65536. It does not mean an image displayed on the screen will have such number of gray levels. Video input grayscale determines the maximum number of gray levels can be represented in the image on the screen. Video input grayscale also refers to as color depth, which is measured in bit. 8-bit equal to 255 gray levels, and 10-bit equal to 1023 gray levels. Video input gray level is usually 8-bit or 10-bit. 12-bit is still very rare in the market today. If the input grayscale is 8-bit, which is 255 gray levels, and output grayscale is set to 12-bit, that is 4095 gray levels in the software, the screen can only display 8-bit gray levels eventually because the video source is 8-bit. In conclusion, the higher grayscale we set, the larger range of output gray levels available to output, and more details of the image can be presented on the screen. It doesn't matter all output gray levels we set. The gray levels are actually presented on the screen will be still 255 if the input is 8-bit. The LED screen itself cannot represent additional gray levels more than the source. So now you would understand 18-bit color branded in the industry is actually the marketing term, because most of driver IC only support 16-bit gray levels. Now we know the grayscale is essentially the possible brightness variations range from the darkest to the brightest of a LED. So how the LED produce different brightness level or gray level? In the beginning, we discussed LED screen's working principle. LED is not illuminated all the time. They are actually on and off in different combinations to be represented as an image. The LED control system controls the amount of time that LED is on or off to create different brightness level or gray level. The longer on time of LED, the brighter it will be perceived by the eye. Please look at this example here. There are 4 LEDs. The first LED display gray level 1. Its on time will be very short, and the human eye would perceive it as very dark brightness. If to display gray level 4, a human eye would perceive it as very a little bit darker than gray level 1. The same principle for gray level 16 and gray level 64. And other gray levels. The amount of time of an LED needed for representing the gray level 1 is also called minimum OE. And the next, let's take a deep dive into refresh rate. Refresh rate in LED screen industry is not the same with what we usually use to describe your computer monitor or TV's refresh rate. In general speaking, refresh rate is the number of times that a frame repeats on the display. But when we're talking about LED screen's refresh rate, it refers to the number of times that a LED can produce the highest gray level in a second. It's very tricky. For example, if the LED screen refresh rate is 38 to 40 Hertz and its gray level is set to 4096, in this case, the refresh rate means the LEDs can represent 4096 levels of gray in a second, 38 to 40 times. The higher refresh rate, the LED flashes faster in a certain period of time, and your eye perceives smoother image displayed on the screen. This is the reason why your eye will perceive flickering if the refresh rate is too low, because LEDs is not flashing fast enough to trick your brain or your eye. On the other hand, the highest refresh rate is related to the grayscale. The higher grayscale, the longer the time of LED to produce the grayscale, the less number of times that the highest gray level can be presented in a second. So increase LED screen's grayscale would lower its refresh rate. DCLK and GCLK are two of the most frequent questions I get asked all the time. DCLK refers to data clock It determines the data transmission speed from the receiving card to the driver IC. GCLK refers to Grayscale clock. It determines the data transmission speed from the driver IC to LEDs. Regular driver IC does not have GCLK. The LEDVISION software will not show up GCLK option as well if you are using a normal driver IC. PWM driver IC will increase the screen's visual refresh rate because it divides LEDs on time for a frame into multiple equal time pieces to improve screen's visual refresh rate. If your LED screen is using a regular driver IC, you can increase the DCLK to get a higher refresh rate and brightness, because the driver IC receives more data in a certain time of period, and it will make the LEDs flash fast and larger amount of time that LED stays on. The parameters in this circle are interacting with each other. The DCLK will affect refresh rate and brightness and grayscale and the limitation of the horizontal pixels that is driven by a single receiving card. The grayscale affects brightness and the refresh rate. The refresh rate affects brightness. The number of horizontal pixels affects all those four parameters. This sounds might be a little bit convoluted, but adjusting LED screen's performance is essentially finding the balance between these parameters. So understanding these parameters would also greatly help engineers to do troubleshooting in the field. If you play with these parameters in LEDVISION software sometime, you will notice this is not that hard actually. Next, we will get into LEDVISION and look where these parameters in the software. Other than I said, LEDVISION is an engineering software, is not recommended for integrators and end users. I'm gonna quit my PowerPoint and launch the LEDVISION software now. Just give me a second. This is the LEDVISION software. Its version number is on the top left. The latest version is 6.9. And we can see a navigation menu on the top. And these small buttons here are the shortcuts. Because our object today is to go through the advanced parameters in LEDVISION software, so we will not go into details of how to use LEDVISION software. We can click this button, LED screen settings, to get into the advanced tab. And after we click this, it will pop up a password window. Type password 168. 68. There are three tabs on the top: sending device, receiving card parameters, and the receiving card mapping. All we're going to look is receiving card parameters. There are basically four sections in this page. The module information. This information will be created once you've done the intelligent setting. Intelligent setting is actually to create a parameter file in the factory and we usually don't do this procedure intelligent setting in the field. This process has to be done in the factory. And the section lower than module information is the cabinet settings. We can see the cabinet's width and height. This is not really the cabinet's information. It's the receiving card, the pixels that are controlled by a single receiving card. As we all know, some narrow pixel pitch cabinets has 2 receiving cards in a single cabinet, so this is not quite correct. And the third section here is the performance setting. This is what we're going to look today. In the performance setting, we can set up a refresh rate, and we can set up the gray levels, the DCLK, and other information such as calibration mode. We can disable the calibration or enable brightness calibration, chroma calibration. We can choose where to get this calibration data, from the module or from the receiving card. And we can choose to black out the screen when there's no signal received from the sender, or keep the last frame, or just play offline. This option is reserved for a very special type of receiving card. And we can choose the receiving card input card depth, and we can edit the gamma value. This is the gamma curve, or we can choose custom the gamma. If you want to edit by gamma table, we can click this button. And the bottom section here is to read or send configuration file. We can click read button to read the configuration file from the receiving card, or we can click the load button to load a existing configuration file from your computer or your USB flash driver. And we can save the current configuration in the software to local storage. And the send button is just to preview the configuration. It's not really send the configuration and save the configuration to the receiving card. Save to receivers is to save the configuration to the receiving card. And once you hit this button, even if your power cycle your LED screen panel, the receiving card will be not resetted. I mean, the configuration file will be not resetted. This page may varies depending on the type of driver IC you are using. Now I'm using SUM 2017 driver IC. This is a regular driver IC, it's not PWM driver IC. And if we can try to set up its grayscale. Its current grayscale is 16,000 around, and we can set it up to 65536, which is 16-bit. Once we set up the gray level to 65,000, its refresh rate will be lowered to 960. Let's look over again. So if we lower the grayscale, we will get a higher refresh rate with a regular driver IC. The DCLK is the data transmission speed from the receiving card, from the receiving card to the driver IC. Let's see what will happen if we increase the DC clock. $17.9, $20.8. You know it. I don't know if you notice that if I increase the DCLK, this number is changed. For example, now it's 276 at 20.8. If I increase it to 25, it becomes 332. This is the limitation of the pixels in horizontal can be driven by a single receiving card. And if I increase the DCLK, you will be able to choose a higher refresh rate up to 2880 in this configuration. And if I increase the refresh rate, the limitation dropped to 214. And its brightness is decreased to 58%. I'm gonna do it again. We lower the refresh rate, you got higher brightness percent, is 77%. We increase the refresh rate, the brightness dropped. And if we increase the gray level, the refresh rate dropped. It's actually not very hard to adjust these parameters. All you need to do is just find a balance between these parameters. And if you play with LEDVISION software sometime, you'll understand how these things works. As I mentioned earlier, I planned 2 classes for advanced parameters adjustment and LCD screen performance setting. This is our first class, and I will prepare another in-depth performance adjustment in our second session. So this is gonna be all for today. And if you have any questions, please type your questions in the chat.